Good morning, good afternoon, or good evening. Today, we're going to look at an important property of continuous functions called the intermediate value theorem, and I think we should just jump in. Suppose that f is continuous on the closed interval from a to b. It could be continuous in other places as well, but we just need it to be continuous on a closed interval. And let capital N be any number in between the function values f of a and f of b, where f of a is not equal to f of b. So we just need the function values to be different on the endpoints of this interval. If all of that is true, then there exists a number c between a and b such that f of c equals capital N. Now, this is a type of theorem called an existence theorem, right? It says there exists a number c. It tells us that there must exist a number, but it doesn't actually tell us how to find the number. That might seem weird to you. Maybe you haven't seen existence theorems before, but there are certain situations where just knowing that something exists helps us to prove something bigger. Now, before we go and actually apply this theorem for something, I just want to show you a graph so you can see what we're looking at here. Okay, so here we have a function. This is y equals f of x, which I suppose I could have labeled. And we can see that this is a continuous function on the closed interval from a to b. We know it's continuous everywhere on that interval. It could actually continue further out. Doesn't have to. It really doesn't matter either way. We just need it to be continuous on that interval. And what this says is that if we pick any number, capital N, that's between f of a and f of b, so any y value in between here, for example, we could say that n is this value. For any n between f of a and f of b, there exists a number c somewhere in between a and b, such that the function value at c is equal to n. And in fact, if we draw a horizontal line at n, for this particular value of n, we can see that there are three different places where the function has a value there. So we could even call these C1, C2, and C3. It doesn't say there's only one number c. It says there exists a number c. So there's at least one value that has a function value equal to n. Basically, this means there's not going to be a gap. We would need a discontinuity to skip a certain function value between f of a and f of b. Right? If we picked a second n value, I'm just going to call this n2, for example. In this case, we can see there's only one x value that gives us a function value of n sub 2. So there might be more than one, but for any value of n between f of a and f of b, basically we know the function has to cross it at least once. And this is a property of the function being continuous, right? If we had a similar graph where the function was not continuous, this would not necessarily be true. Okay, here is another example of a function where f of a is f of a and f of b is f of b. Very similar, but here we have a discontinuous function. If we have a discontinuous function, it's possible to pick a value of n where n is not a function value for that function between a and b. And that happens because of the discontinuity. But if we have a continuous function, we know that when we're drawing the graph of a continuous function, we don't pick up the pencil. There's no breaks. And so If we want to start down here at f of a and end up at f of b, of course we're going to have to cross any line in between those two. Now let me show you how this can be very useful. We want to prove that the equation x squared equals x plus 1 has at least one real solution. Now we can do this, first of all, by moving around some of the terms of the equation so that one side is equal to 0. If we subtract x and 1 from both sides, this is the same as x squared minus x minus 1 equals 0. I've just moved all of the terms to the left-hand side. And what we're going to do then, the left-hand side, we're going to name that f of x. And so the original equation has a real solution so long as our new function has at least one 0. It's equal to 0 at one point. And so here's the neat thing. This is a continuous function on the real numbers. And so we want to show that it has at least one real solution. If we can find an x value that gives us a function value that's negative and another x value that gives us a function value that's positive, we know that in between those two x values, that function is going to have to cross the x-axis somewhere because it's continuous, and wherever it crosses, that is going to be a real 0 for the function and thus a real solution for the equation. We won't be able to find the exact value of that, but we will be able to prove that there's at least one real solution. So let's make a table of values for our function x and f of x. And I think plugging in 0 is always the easiest. And then also small numbers are easy to plug in. So we can try 1, 2, and 3 and see if we get anything good. Now let's evaluate this function for each of these numbers. If we evaluate this function at 0, we get 0 squared minus 0 minus 1. Actually, I can write that out here. 0 squared minus 0 minus 1. And of course, that's negative 1. So that's pretty easy. Let's evaluate it at 1. It's going to be 1 squared minus 1 minus 1. So that's what? 1 minus 1, which is 0, minus another 1, which still gives us negative 1, so that's not helpful. But let's try 2. 2 squared minus 2 minus 1. 2 squared is 4. We've got 4 minus 2 minus 1. 4 minus 2 is 2, and 2 minus 1 is positive 1. And so because we have one value that gives us a negative number and another value that gives us a positive number, by the intermediate value theorem, that tells us that we have to have a 0 of the polynomial in between these two. And we said that a 0 of the polynomial would give us a solution to the original equation. So the intermediate value theorem, the IVT, tells us there must be a real solution between 1 and 2. And if you're not quite following how this works, let me give you another quick drawing. We don't know what the graph of this function looks like, but we do know that when x is 1, f of x is negative 1. So that's going to be a point down here. And then when x is 2, f is positive 1. So that's going to be a point up there. And because this is a continuous function, we know that somewhere this graph is going to have to cross the x-axis. If we go from this point to this point and our graph is continuous, we don't know exactly how the graph will look like, but we know it must cross the x-axis at some point. Wherever it does cross the x-axis, that is a 0 of the polynomial, which means that x squared minus x minus 1 is equal to 0, but this equation is equivalent to that, so any solution here is going to give us a solution there. This is really helpful if we want to figure out whether or not a function has a real 0, or whether or not we want to determine if an equation has a real solution. Being able to set up a table of values like this and try some values can help us confirm if a continuous function does have at least one solution.